Hi all. In this lecture, we will discuss a recursion formula for finding the GCD of three or more positive integers. Okay. So before going to the calculation, recursion formula for calculation, we first define extend the definition of linear combination. That is linear combination of n positive integers. Okay, the definition is like this: a linear combination of n positive integers a1, a2, etc. an is a sum of the form alpha 1 a1 plus alpha 2 a2 plus etc. plus alpha n an, where alpha 1, alpha 2, etc. alpha 1, alpha 2, etc. Alpha n are integers. Okay, so this is the definition of n linear combination of positive integers a1, a2, etc. an. Okay, for example, a linear combination of 12, 15, and 21 is minus 1 into 12 plus 1 into 15 plus 0 into 21. Now next theorem, we extend the definition of GCD into n positive integers. The GCD of the positive integers a1, a2, etc. an is the least positive integer, that is a linear combination of a1, a2, etc. an is the least positive integer, that is a linear combination of a1, a2, etc. an. This is actually theorem 3.9. So the illustration, we need only the statement. The illustration of the theorem is for example, consider the question: express the GCD of 12, 15, 21 as a linear combination of 12, 15, and 21. Okay, so among this, we know 12 is the simplest one, and the factors, among the factors of 12, 3 is the largest common factor among them. So GCD of 12, 15, 21 is equal to 3. Now we have to express 3 as a linear combination of the sum of these three numbers 12, 15 and 21. We can write simply it as 12 into minus 1 plus 15 into 1 plus 21 into 0. That is 3 is equal to some alpha 12 alpha plus 15 beta plus 21 gamma, where alpha equal to minus 1, beta equal to 1 and gamma equal to 0. Okay, this is the illustration. Next we move to the recursion formula for finding the GCD, recursion formula of GCD. Okay, it is stated as a theorem. Theorem number is theorem 3.10. Let A1, A2, etc. An be n greater than or equal to 3. B be n positive integers. Let a1, a2, etc. n be n positive integers. Then result says that GCD of a1, a2, etc. an is equal to what? GCD of, in bracket there is a GCD of a1, a2, etc. up to an minus 1, comma an. So using this recursion formula we can find the GCD. So for convenience we name the GCDs. Let D is equal to GCD of A1, A2, etc. An, and let D dash is equal to what? GCD of A1, A2, etc. An minus 1, and D double dash is equal to GCD of D dash comma An. And we will show that we have to show that we have to show D is equal to D double dash. For this, by the property of congruence, by the property of divisibility, we need to show that D divides D double dash and D dash divides D. Then we can prove the conditions. Okay, so this we have to prove. D is equal to, we have taken D as the GCD of n positive integers, and D dash is the first n minus 1 positive integers, and D double dash is actually D dash plus an. Okay. Okay, then first we show that D divides D double dash. For that we know that D is equal to, since D is equal to GCD of A1, A2, etc. AN, we have D divides AI for every I. That we know. So D divides AI for every I. So this implies D divides D dash, where D dash is the GCD of A1, A2, etc. AN. Since D divides A1, D divides A2, etc. D divides AN minus 1, we can say that D is a common divisor of A1, A2, etc. Common divisor of A1, A2, etc. AI. So D divides, we can say that D divides D dash. Since D dash is the GCD of A1, A2, etc. AN. And also we can say that D divides AN. So D divides D dash and D divides AN. This implies D divides GCD of D dash comma AN. Okay, so D divides GCD of D dash comma AN. This implies D divides D double dash. Okay, let this be equation number 1. So D divides D double dash is obtained. Now we need to show that D double dash divides D. Now we need to show this one. D double dash divides D. For that we know D double dash is GCD of D dash comma AN. So since D double dash is equal to GCD of D dash comma AN, we can say that D double dash divides D dash and D double dash divides AN. Okay, but D double dash divides D dash implies D double dash divides AI for every I or less than or equal to n minus 1. So for 1 less than or equal to I less than or equal to n minus 1. And that means D double dash divides AI for 1 less than or equal to n y less than or equal to n minus 1. That means D double dash divides A1, D double dash divides A2, etc. D double dash divides AN minus 1. And we have D double dash also divides N, and D double dash also divides N. So this implies D double dash divides GCD of A1, A2, etc. AN. This implies D double dash divides D. Let this be equation number 2. So from 1 and 2, by the property of divisibility, D double dash divides D and D divides D double dash implies D double dash is equal to D itself. Therefore, the recursion formula says that GCD of A1, A2, etc. AN is equal to A1, A2, etc. AN minus 1 GCD of comma AN. So this is the recursion formula for finding the GCD of n positive integers. So let us look at the one example. Using recursion, evaluate GCD of 18, 30, 60, 75 and 132. Okay, this we have to evaluate using the recursion formula. So GCD of 18, 30, 60, 75, 132. By recursion formula, this is same as GCD of 18, 30, 60, 75, comma 132. Now again applying the same recursion, we will obtain this as GCD of 18, 30, 60, comma 75, comma 132, which is again is equal to GCD of 18, comma 30, comma 60, comma 75, 18, comma 30, comma 60, then comma 75, comma 132. Okay. Then 18, comma 30, 60. Okay. Now 18, comma 30. GCD of 18, comma 30 is 6 into 5 is 30, 6 into 3 is 18. So 6 is the uh, highest common factor, or GCD, greatest common divisor. So 6, comma 60, comma 75, comma 132. So this is equal to 6, comma 60, that GCD is 6 itself, 6, comma 75, comma 132. Now 6, comma 75 is it is 3, 325 into 3. So this is 3, comma 132. What about 3, comma 132? Now 132 is a multiple of 3 itself. Therefore this is equal to 3. Okay, this follows. So this is an illustration of the theorem. Now we have two corollaries. Corollary 3.5. This states that if D is equal to GCD of A1, A2, etc. An, then D divides AI for every integer I. If D divides GCD of A1, A2, etc. An, then D divides AI for every integer I. Where 1 less than or equal to I less than or equal to N. So this is our first corollary. Then second corollary is if D divides the product A1, A2, A1 into A2 into etc. into AN, and GCD of D comma AI equal to 1 for 1 less than or equal to I less than or equal to N minus 1, then D divides AN. So this is an extended version of Euclid's lemma. That means if GCD of A divides BC and GCD of A comma B equal to 1, then A divides C. This is an extended version. If D divides a product A1 into A2 into etc. into AN, then D divides and the GCD of D comma AI equal to 1 for 1 less than or equal to I less than or equal to N minus 1, then D divides AN. Okay. So this about the recursion formula for finding the GCD of n positive integers and their corollary. Okay, thank you. Let's stop here. Thank you.